Hello everyone, my name is Chiara Ercolani, and today I'm going to present my work, titled 3D Odor Source Localization using a Microaerial Vehicle, System Design and Performance Evaluation. This work was carried out at the Diesel Laboratory at EPFL in Lausanne, Switzerland. When gas leaks occur, for example in warehouses, environmental emergencies, or search and rescue operations, it is very important to be able to locate the source of the gas leak in order to take fast and effective countermeasures. This operation is usually done using animals, but this puts their lives and the life of the human operation in danger, and it is also very costly. The idea behind robotic olfaction is to give a wide variety of robotic platforms the capability of sensing odor particles in the air, in order to perform tasks such as odor source localization. The biggest challenge of this research field is given by the Plume structure. In fact, even though it can be represented as a time average Gaussian, in reality it looks very filamentous and patchy, and this makes it very hard to sense and to track. Moreover, odor dispersion is a 3D phenomenon, which means that we need to use platforms capable of 3D motion if we want to be more effective in our odor source localization task. Flying vehicles have been used for the task of odor source localization because of their capability of exploring 3D environments. UAVs, in particular quadrotors, have been used because they are very maneuverable, the flight time allows for fairly long missions, and they are able to carry all the necessary equipment to perform odor detection. The biggest drawback of this platform is the propeller impact on the plume. In fact, the propellers actively disperse the plume that contains the odor particles that we are trying to sense. Blimps have also been used for this task. The propeller impact on the plume is almost negligible. The flight time is even better than that of UAVs, but they have two big drawbacks. They are fairly bulky and hard to maneuver, and the size-to-payload ratio is not in our favor. Finally, microaerial vehicles have been employed. They retain the same maneuverability properties of UAVs, but the propeller impact on the plume is much smaller because of their smaller propellers. The drawbacks of this platform are the size of the payload and the low flight time, but this can be enough for indoor application. This is the platform that we chose for our odor source localization experiments in indoor spaces. A few words need to be said about where to place the odor sensor on a flying platform with propellers. A study tried to experimentally determine the best sensor placement, and the conclusion is that it should be as far away as possible from the propellers. However, this is not always possible, because we have to have a mechatronic integration that does not destabilize the flying vehicle. Bottom placement has been identified as a good placement, either when the sensor is directly attached at the bottom of the frame of the robot or hanging from a rope, because the downwashing effect of the propellers conveys odor particles on top of the sensor. However, there is no final consensus in literature about the best placement of an odor sensor on a flying platform. An important class of 3D odor source localization algorithms is that of bio-inspired algorithms. In these algorithms, the robot movement is inspired by natural phenomena. These are good candidates for deployment on flying vehicles because of their low computational cost, the fact that they are very reactive, and the fact that they are optimized for the end goal. There are a few examples of these algorithms deployed on flying robots. However, most of them are deployed on fairly large flying robots that only move on a 2D plane, so they do not exploit the full 3D range of motion of these platforms. There is only one example of an implementation on an MAV that moves in 3D. However, the algorithm is deployed on a very small area, and the starting point is constrained to be inside the plume. An interesting 3D bio-inspired algorithm was developed in 2017. This algorithm assumes that there is a source of odor in the environment and a wind field that displaces the odor particles, creating a plume. The algorithm has 3 steps. The first step is the plume finding. In this step, the robot moves on a crosswind plane with a Levi walk, which is a kind of random walk, to try to sniff the plume for the first time. Once it finds the plume, it tries following it with an upwind surge. If the plume is lost, the robot moves on a spiraling motion, starting from the point where the plume was last sensed. We perform a spiraling motion and not a random walk, because we want to linger around the place where we last sensed the plume, to increase the chances of reacquisition. Plume following and plume acquisition together form a second step of the algorithm, which is plume tracking. Finally, when the robot is inside a small volume around the inlet, we declare that we found the source, and we consider the run a success. Although this algorithm gave very good results, it was only tested with a robot mounted on a 3-axis manipulator. So this is not suitable for real deployment, and it does not address the challenges of deploying such algorithm on a flying platform. The biggest challenge when performing odor source localization with a flying vehicle is the impact that the propellers have on the plume. Moreover, the flight time is low, and we do not have a reliable simulation that takes into account the interaction between the plume and the propellers, so we cannot test the algorithm in simulation beforehand to calibrate key parameters. To take into account these challenges, we adapted the algorithm that I described before. First of all, we continuously move and sample, instead of stopping at every algorithmic step to gather samples. We do this to respect our flight time budget. Moreover, we use a different aggregation criteria for our odor samples. In fact, we do not take the average over the last few samples, but we take the maximum value over the last few samples. Although averaging is a very effective method to improve sensing in a noisy setting, in this scenario it is more important to avoid missing a cue about the presence of the plume. We perform denser spiral movements because we want to linger for a longer time around the place where we last sensed the plume. And finally, we use a fixed odor threshold to determine whether we are inside or outside the plume. This value, together with other key parameters of the algorithms, are found experimentally. The platform that we chose for our work is the CrazyFly robot. It is a small-dimension micro-aerial vehicle, and it is ideal for repeatable work in indoor spaces. Its open-source hardware and software architecture make it very nice to use for research applications. This platform has been successfully used for chemical sensing in literature, and we developed a custom PCB board with a VOC sensor that allows us to sense odor particles in the air. The biggest limitations of this platform are the flight time and the payload size, but as I said previously, these are enough for our indoor mission. We conduct our odor source localization experiments in a wind tunnel. The usable volume inside the tunnel is smaller than the total volume because of localization constraints. Inside the tunnel, we can adjust the speed of a laminarized wind flow. We use two different localization strategies, either an ultra-wideband localization system with 8 beacons or a motion capture system with 13 cameras. We use either one of these two methods because we want to see what effects a different localization strategy has on the outcome of the odor source localization algorithm. Finally, we use an electric pump to disperse a mix of ethanol and air in the wind tunnel to create the odor plume. For the experimental evaluation of our odor source localization algorithm, we start with a sensor placement comparison. We put the odor sensor on top and at the bottom of the CrazyFly. These are the easiest configurations to achieve. And we try to see which one gives the best sensing results. And we select this for the second step of our experimental evaluation, which is a performance evaluation under varying environmental conditions. We change the wind speed and the source release rate according to the 4 setups that you can see in the table. And we try to see how these two environmental parameters impact the outcome of our algorithm. Finally, we want to see what is the impact of a different localization strategy on the outcome of the algorithm. So we repeat the performance evaluation described before, using either an ultra-wideband localization system or a motion capture system. We use two evaluation metrics to evaluate the performance of our algorithm. The first one is the success rate, which is the number of successful runs divided by the total number of runs. The second one is the distance overhead, which is the distance traveled during one run, divided by the upwind distance, which is the shortest distance between the starting point of the robot and the position of the source. Now I'm going to present the results of our experimental evaluation using an ultra-wideband localization system. From our sensor placement results, you can see that when the sensor is at the bottom, the success rate is 100%, compared to 80% when the sensor is on top. Moreover, the distance overhead metric is lower and has less variability, indicating better performance. So, sensor at the bottom is the configuration we chose for our performance evaluation. In all 4 scenarios, we had 100% success rate, and we had good performance with extraordinary performance for setup A, with high wind speed and high release rate. Setups B and D present a high variability of data, and they are the ones with a low wind speed. This can be explained by the fact that when the wind speed is low, the plume is less pointy and more spread in the environment. Moreover, setups C and D with low release rate have a higher distance overhead metric. This can be explained by the fact that when the release rate is low, we are dispersing less odor particles in the air, and it is harder for the robot to sense them. Here is a video of one run using the ultra-wideband localization system. Initially, the robot performs a levy walk on the crosswind plane to try to sense the plume for the first time. Once the plume is found, the robot follows it using an upwind surge and a spiraling motion to reacquire the plume in case it is lost. And finally, the robot finds the source. And now a video of a run using motion capture system. You can already see from the initial levy walk that the movement of the robot is much cleaner. And the robot will sense the plume again and move with an upwind surge. And now you're going to be able to see very clearly a spiraling movement. And finally, the robot finds the source. Now I'm going to present the experimental evaluation results when comparing an ultra-wideband localization system to a motion capture system. On the left side of the slide, you can see that the distance overhead metric for the 4 different setups and for the 2 different localization systems follows the same trend. However, the motion capture system distance overhead, which is in red, is always lower, indicating better performance. On the right side, you can see the tracking of the movement when using ultra-wideband and when using motion capture system. And again, you can see very clearly the smooth movement of the motion capture system compared to the more jerky movement of the ultra-wideband localization. Although motion capture system gave better results, ultra-wideband is a much cheaper and easier to deploy solution, so it should be considered for future applications. Thank you very much for your attention. For more information, you can send me an email at chiara.ercolani@epfl.ch, or you can visit our website.